Hi, my name is Georgi Radulov and I would like to show you how to simulate and implement and measure nonlinear gain stage. Nonlinear gain stage is needed for various applications, among which are the RC oscillators. We want to use nonlinear gain in RC oscillators as the feed-forward gain, and the nonlinearity of this stage will determine the amplitude of the oscillations. But let's start. First, we can design our stage, our gain stage in multisim. So here is a schematic which I prepared, and this is a simple stage of non-inverting amplifier with a gain of 3. And in the configuration like it is, nothing special about it, it's just gain of 3. How we can determine this? We can run DC simulation, DC sweep simulation. From simulate you click analysis and simulations, and here you select DC sweep. Then just let me show you here. I have a DC signal source called Vin, and then I can select it from here. And then I say to I instruct the simulator to sweep this signal source from -2 volts to 2 volts in steps of 0.01 volt. As an output, I would like to see V out. So here all the nets in the circuit, and I can select V out. And now I click run. And this is it. So what I see here is a slope. This is the input sweep of the signal, and this is the output voltage. And the slope is 3. And this is the gain of the non-inverting stage. And this is linear gain. So the gain is constantly 3. It is determined by the feedback resistor and the resistor to ground. 1 plus the ratio of these two is 3. Now, if I want to have nonlinearity in this characteristic, transfer characteristic, I need to realize certain clipping. And this clipping can be done through these diodes. So basically, if I connect the diode, so let me see, here at this point, and this in this point, and then this here and this here. Now the clipping network is activated. It works as follows. If the voltage, forward voltage across the diode is about 0.7, then the diode becomes like a closed switch. This means that this resistor of 1 kilo ohm will be connected in parallel with the feedback resistors, which will cause that the gain of the stage will drop, because the gain of the non-inverting amplifier configuration, which is 1 plus the feedback resistor divided by the resistor to ground, will be reduced, since the feedback resistor, the effective feedback resistor, will be R2 plus R7 in parallel with R4. And then we connect in parallel a small resistor of 1 kilo ohm in parallel with the feedback resistor of 20 kilo ohm. Effectively, this will be a very small value, less than 1 kilo ohm, which means that the gain of the stage will drop to about something a little bit higher than 1. Now let's see, we rerun the simulation and we look at the DC sweep, and this here is the nonlinearity that we just introduced. So this is the linear gain of 3, and at this point the diodes activate. For this point, this diode is responsible, and then it connects R5 in parallel with the feedback resistor R2 and R7, and then we have a reduction of the gain. For this point, this diode is responsible, and then the gain is reduced. If we use this configuration in an oscillator, we can determine these points as the amplitude of our oscillation. We want to implement this on a breadboard and measure it with the MyDAQ. So I'll use for the amplifier 741. This chip, and I connect it to the breadboard. And the important thing to note is pin number 1. Pin number 1 is indicated by this dot here. Where the dot is, there is pin number 1. So now it is important to know what are the pin configurations of the chip. You can see that here, so they're easily found in internet. And I put this picture as background image. So inverting input is pin number 2, non-inverting input is pin number 3. Here, this is the negative power supply, this is the positive power supply, this is the output. This is how I have to connect it. For this I will use, so now for power supply and for measurements and stimuli, I will use the MyDAQ. Here it is. You can look at the input configurations and the signal that I can generate, but this here I can use for the power supply, for the plus 15 volt and for the minus 15 volt. This will be in the middle and this will be used for the ground. Then I'll use this as the input signal, and I'll use this signal to measure. Now you can see the configuration. In the configuration, the output is single-ended, while to measure something it's differential. And I will need single-ended measurements. So this is why I already here at the level of the MyDAQ connected a common ground. And this goes one cable, the black one, will be the analog ground, which is connected to the analog ground here locally of the input, which is connected locally to the analog input minus 0, and locally to the analog input 1, the negative input. Then I connect the signal source, which is, in my case, what I use is just a second, analog output 0. I connect it locally to the analog input 0 plus, which means that when I monitor the inputs of the MyDAQ, the analog input 0 plus will always give me the signal that I generate from the signal source. And then I will use the other analog input 1 plus to measure my single-ended signal which I want to measure. So this is the configuration in the MyDAQ. You can pause the video and take a look exactly at my configurations. I hope that it is clear. And now I'll make my first connections. So this will be 0, the black one will be the 0, the signal ground, and I'll use this rail for this, here, like this. This is the plus 15 volt, I'll use this rail. and this is the minus 15 volts, and I'll use this rail. Right. Now I need to build the circuit, so it is always good to measure exactly the resistors that you're putting to avoid mistakes. So you can use MyDAQ for this. In digital multimeter configuration. So I'll connect now MyDAQ. This is the signal ground, so I'll just connect it here. Alright. Now I can select digital multimeter. So this is digital multimeter, and I just want to check the resistances which I'll put in my circuit. Second, I have to run it here. Yes. It's about 10. Good. So this is 10. Ten. .9. So to not be exactly 10. So if you really want to make a precise gain, you have to choose your components. I'll work with this, so I can realize a gain which is a little bit higher than 3. So this resistor I'll use as the resistor to ground. So from the inverting input to ground. Inverting input is pin number 2. So this is pin number 2, and this is my ground node. So this will be a configuration like this. Like this. And then I'll use these for the feedback from the inverting input to the output. Output is pin number 6. So, and then I have 2 in series because I want to make 20. So this will be configuration something like this, first step. And then from here to the pin. The connection should be stable. Something like this. Now, next step is to power the amplifier. I have to connect the power supply. The negative power supply is pin number 4. I have to connect it to minus 15 volts, which is this rail. So number 4 is from here, and I have to connect it to the negative, -15. And then the positive power supply is pin number 7, and I connect it to +15 volts. Pin number 7 is here. So now this should give me a linear gain of 3, or a little bit more than 3. So to measure it, so this will be my stimulus, and then I have to put it in the non-inverting input, pin number 3. Yes. And this will be my output, pin number 6, which I will measure. This pin here. This. Alright, so will this work? Okay, so this is my file, and now let's measure this. So I need an input. I will use the arbitrary waveform generator. Have to configure it. So I will use analog output 0, and then I have to select what is the waveform, and I can select triangular. Then I will need an oscilloscope. And these are the two channels that I will be monitoring. One will be input, the other will be output. So I will run this. This is the signal that I'm inputting, and I will run the oscilloscope, and so this is it. Here I can control the time scale, and here I can control the amplitude. So you see, I'll just stop it to analyze it. This is a gain of 3. So this is the input amplitude, and then it's 1, 2, 3. You can see here that I can also control the gain from the arbitrary waveform generator. So now I'm changing the gain, and you can see here the response. Alright, I'll stop it now. This was the easy part, because this was just the forward gain. Now I'll apply the clipping to realize the nonlinear gain. So let's first start with connecting the 1 ohm resistors from the output. Now the output is here. Then if I connect them to this node, and then if I run again the signals, nothing should be changed. Just my next step is to connect the 15 ohms to I'll connect now 50 ohms to the positive and the negative power. So let me check first the 15 ohms. Kilo ohm resistors. A little bit higher. A little bit lower. Yeah, these are the values that I have, so I have to live with these. Let me Alright, so as you can see, if I measure at the output, or at the output not I change nothing, but if I measure now at the node between the 15 kilo ohm and the 1 kilo ohm resistor, I should see a scaled version of the signal. Here it is. So it is shifted version. Yeah, also there is a scaling. So this will be the version which is scaled down because it's between a resistive divider, voltage divider between the output signal and the negative power supply of minus 15 volts. And this node here should be the equivalent, but for the positive power supply. Here it is. So this is the upper point of the voltage divider, and the other was the bottom point of the voltage resistive divider. Now my next step is to connect diodes, which will actually activate if the amplitude becomes too large. So now we'll connect the diodes. I'm measuring here the output, and you can see the signals, the input and the output signals here. The green is the input signal and the blue is the output signal, and I have an amplification of about 3. And now I connect, so this is without diodes, and now I'll connect the diodes. So this is to clip the bottom part. So one diode now is connected. Nothing changes in the waveforms because the amplitude is small. But now if I increase the amplitude, now if I increase the amplitude here through the gain, I'll reach a certain point for which the output signal is too high, and then the diode starts activating. You see that it works. This diode works only for the bottom part of the input signal. And here I have the compression. The gain is limited. The output signal is clipped. A little bit of more gain in the input. Yeah. You see how the output is clipped. If I now connect the other diode, it will be clipped on both sides. Here it is. Now you see that the output amplitude is clipped and you can clearly see the compression. I can illustrate this. Let's investigate this. Let's take here it is. So I have a gain of 3, and at this point when the amplitude becomes too high I'll have a gain of less than 3, and this is for the bottom part. Keep in mind, so I will now reduce the gain. So if I reduce the input signal, you can see that now there is almost no clipping. Now the clipping is here. Here I operate in the linear region of my transfer characteristic. Here is the transfer characteristic. So here at the moment I'm with the signal in this region, but let me get to 1. Here now the input is 1 and I already have the compression. So you see the compression here at the output signal, the blue signal. These are these points in the transfer characteristic. Here now I reduce the amplitude of the input signal. And now, oops, the amplitude is 0.8, 0.7, 0.6, and here I approach the linear region. If the input is 0.3, about 0.3, then I'm in the linear region. Here you can also test this with different signals, for example sine wave signal. You see the compression. If I increase the amplitude, I have the output signal, a tone, but with a lot of harmonic distortion. Now my input signal is in the linear characteristic here, and if I increase it further, the peaks of the signal, the output signal, exceed these points here, and I have the compression, the nonlinear gain. This is where my gain reduces. Thank you very much for your attention.